Completing the square. Why is completing the square so important? I'll explain that later on in the video. However, first, let me show you how to convert a quadratic form into a completed the square form. A completed the square form looks like this. A bracket x plus b squared plus c, where a, b, and c are just random numbers. Okay? Now here is a normal quadratic, x squared plus 4x plus 7. And I'm going to show you how to convert this into a completed the square form. First, what you want to do is, since a is equal to 1, okay, a being, we're taking this from the normal quadratic form, ax squared plus bx plus c. This means that a is 1, b is 4, and c is 7. Now, because a is 1, we can do this. I'll explain what we do when a is not 1. Okay? So we take the value of b and we divide it by 2. So 4 over 2 is 2. Now this goes inside of the squared part. So we get x plus 2, 2 being from here, squared. Okay? Now let's quickly expand this. And if we expand it, we get x squared plus 4x plus 4. And look, we have the x squared part from the original equation, and we have the 4x part from the original equation. However, here we have a plus 7, and here we have a plus 4. So in order to go from x plus 2 squared to the original question, we have to add 3 more to the end. Okay? Look, so this part right here is equal to the x plus 2 squared. And we have to add 3 more to get the original equation. So I added 3 more. Now look, this is the completed the square form. Okay, let me write the form down here. ax plus b squared plus c. And a would be 1, b would be 2, and c would be 3. Okay? Now, what if we do if a is not equal to 1? Let's do 2x squared plus 8x plus 10. Okay? What we do is we factor out the 2 from the first x squared term and the x term. So we'd get 2x squared plus 4x, closing bracket, plus 10. And if we distribute the 2, we get 2x squared plus 8x plus 10. So we've changed nothing so far. Okay? Now, we want to do the same thing that we did before. We take the coefficient of just x, and then we half it. And in this case, if we half it, we get 2. So we have 2 bracket x plus 2 squared. Okay? And if we expand the x plus 2 squared, we get x squared plus 4x plus 4. Okay? But the thing is, we don't want the plus 4. We just want the x squared plus 4x over here. So what do? We subtract the 4. So we subtract the 4. Okay? So your closing bracket plus 10. Now if you distribute the 2, you get 2x plus 2 squared minus 8, because 2 times negative 4 is minus 8, plus 10. And this is the same as 2x plus 2 squared plus 2. Okay? And look, that's the same as it completed the square form. ax plus b squared plus c. Okay? Let's go over a few more examples of the completing the square form. Say we have, let's do 3x squared plus 9x plus 14. Okay, again, we factor out the 3. Okay, because we would just want x squared plus a value of x. Factor out the 3. Okay, see, we've changed nothing because we times the 3 again, we get the same as the original equation. Okay, now we do the same thing. We take the value of the x, the coefficient of x, and we half it. In this case, we get 3 over 2. So we do x plus 3 over 2 squared. Okay, now we want to see what we want to subtract or multiply. Sorry, not multiply. We want to see what we subtract and add just to get the x squared plus 3x part. So let's expand this. We expand it, we get x squared plus 3x plus 9 over 4. If you're curious to see how I got that, we do x here and we have 3 over 2 here, x and 3 over 2. We get x times x is x squared, 3 over 2 times x is 3 over 2x, x times 3 over 2 is 3 over 2x again, 3 over 2 times 3 over 2 is 9 over 4, and then we add up the terms, so we get this. Now look, we have the x squared term here, we have the 3x term there, but we don't want the 9 over 4 part, so we have to subtract the 9 over 4. Okay, so we don't have this part anymore. However, one thing that's important is that this stays within the bracket of the 3. Okay, that's very important. Now this equals to just the x squared plus 3x part. But we also want a plus 14. So we add 14 to the very end. Now if we expand this out again, we get 3x plus 3 over 2 minus 3 times 9 over 4 is 27 over 4 plus 14. So we have 3x plus 3 over 2 squared. What is 14 minus 27 over 4? So 14 times 4 is 56. 56 over 4, 27 over 4. And 56 minus 27 is 29. Yep, 29 over 4. And there we have it. This is the form of ax plus b squared plus c. Okay? Now, why is getting into the completed the square form important? It's important because it allows us to draw accurate quadratics. Okay? So, drawing quadratics. Here we have a standard y is equal to x squared curve. Okay? And if I can plot a few points on, this is 1, this is 1, because 1 squared is just 1. So when x is 1, y is 1. I'll also plot this point. So x is 2 and y is 4. Because 2 squared is equal to 4. So when x is 2, y is 4. Okay? So this is the standard y is equal to x curve. Now, but the thing is, all quadratics aren't just x squared. So let's scroll down a bit. What happens if we change the starting point? What I mean by that is, I can move this up or down. So originally it's here. If I move it one block, one space, one unit up, what has happened? Every single value has increased by 1. So the output of the function, aka the y value, has just increased by 1. So I could just add 1 to everything, and we get this curve. Y is equal to x squared plus 1. What if the curve is like instead of from the origin, what if it's 2 down? Like this. So starting from the origin, we've gone 2 spaces down. So it starts at -2. Since everything has gone 2 spaces down, we're just taking away two values from every single normal x squared curve. Okay? See, if I've got the normal x squared curve, and I'm just moving it 2 spaces down. Now, what if I want to change the starting point along the x and along the along the x-axis? So, if I move 1 to the side, view it as we are delaying the x squared curve. We are doing everything 1 square later. Okay? So, instead of the output of when x is 0, we want to do it when x is at 1. So how can we do this? If we start 1 block later, okay, I could subtract 1 to the value of x. Now, why did I just do this? When x is 1, we just get 0 squared, okay? Which is, if we look at our normal x squared graph, 0 squared is right here, okay? When x is 2, we sub in 2, 2 minus 1 is 1. We just get the value of 1 squared, okay? We are just delaying what we do to x by 1 unit. Okay, and we're subtracting 1 to like counteract that delay. Hopefully that makes some sense. What if instead of 1 block forward, it's 1 back? Okay? Then, since whatever we're doing to x is happening earlier, it would be x plus 1 squared. Because when x is at -1, -1 plus 1 is 0, we are doing what would normally happen to x when it's at 0. See, when x is at 0, that's when y is 0. So when x is at here, but with this equation instead, when x is at -1, y is at 0. And the plus 1 here is illustrating the movement back to the original x squared graph. So we can view this part, the x plus 1 part, as say like z. Okay? So it's like z squared. A bit like the x squared. What if I do 3 forward? 3 forward, that means I want to do it 3 steps, do everything 3 steps later. So I do x minus 3 squared. Okay? So wherever the center point is, say it's labeled as A, the curve would be y is equal to x minus A squared. Okay? And for changing along the y-axis, say we're starting at B, actually no, sorry, C. So we're starting at point C. The curve would be y is equal to x squared plus C. Okay? Now, a combination of these two movements means that we can place our center point anywhere. Okay? So say we have our starting point right here with coordinates 1, 2. This means that we have shifted the normal x squared curve 1 towards the right, and we've seen what happens up here when we shift along the x-axis. We would get y is equal to x. If it's 1 to the right, we just do minus 1 squared. Okay? However, also, and that would result with something that looks like this. as a rough sketch. Okay? However, we've also increased the height of the starting point by 2. You've increased everything forward by 2. Okay? So we add 2 to the very end. Okay? As you've seen over here, and moving along the y-axis. Okay? So now we've been able to map every single x squared graph where the turning point is at any random coordinate. And we do it this, where the turning point is a comma b. Okay? What if we want to increase the slope or even flip the curve? Okay? What we could do is we could multiply the values. Say if we want to increase the slopiness. So instead of like this, you get like something that looks like that. Okay? What we're doing here is we're multiplying the height by a certain value. And the height is just the value of the y-axis. So we're multiplying x squared by a certain constant, let's say a. That's essentially what we're doing. Okay? So it's 2 times as steep. The value of a would be 2. What if we want to flip the normal curve? Let me go back a bit. You want to flip the curve. Every value of y has gone to the negative, right? And how do we get something to the negative? We times it by -1. So in this case, the value of a would be -1. Okay? What if we want to flip it and increase the slopiness by 2? That means we times x squared by -2. Okay? So now we can create any curve, any quadratic curve, by placing a coefficient in front of it. And by using the other rules you've learned. Ax plus b plus c. Okay? And because of this, I've just combined this here with this. And we get a form like that looks a bit like this. Y is equal to a bracket x plus b squared plus c. Now, let's go back to our first example here. When we converted it into a completed square form, we got x plus 2 squared plus 3. What does this tell us about the quadratic curve? Let me draw a set of axes. Okay. So we have x plus 2 squared plus 3. And we know that the starting point would be negative b comma c from here. Okay. This means that it would be, if we take this, x plus 2 squared plus 3, the starting point would be negative 2 comma 3. Okay? So negative 2 and 3, let me just, this is one block is in 1 unit. Negative 2, 3, so the curve would look something like that. Okay? How about for this right here? We get 2x plus 2 squared plus 2. So let's draw a pair of axes again. And we have a plus 2 here. And we have a plus 2 here. That means the turning point is negative b, comma c. And b and c are both 2. So the turning point is negative 2, comma 2. Negative 2, 2. Turning point is something that looks like that. Okay? However, we also have a coefficient of 2 at the front. which means the slopiness has increased. You multiplied every y value by 2. So it looks something like that. Okay? Now, this is the same thing for this one over here. It's again negative b, comma, c is the turning point. The b value is 3 over 2. And the c value is 29 over 4. So the turning point is negative 3 over 2, 29 over 4. Negative 3 over 2, 29 over 4. So the graphs look something like that. Okay? Thank you very much. I hope you enjoyed the video and found it useful. That's all for today.